So now let's talk about terminal velocity. And to do so, we're going to actually tackle, kind of a classical urban legend and debunk it at the same time. So let's say we have the Empire State Building. And the Empire State Building is a height h, where h is about 400 meters. In actuality, it's like closer to 440 or 450. But 400 is close enough, and it's going to make our math work out a bit easier. So then let's say we throw a penny off, and of course the urban legend says that if we drop a penny off the Empire State Building and it lands on somebody's head, then it would be strong enough to kill them. Now, fortunately, this isn't true because people have actually found lots of pennies and stuff that are around the Empire State Building, which means people have actually tested this one out. But let's just see mathematically what would happen. So first, we're going to ignore air resistance. So we say that that the kinetic energy when it gets to the bottom, 1/2 mv squared, is equal to the potential energy at the top. So in other words, V is the square root of 2gh. Again, the square root of 400 is about 20. So this is about 20, the square root of 20 meters per second, which is roughly 90 meters per second. 90 meters per second is pretty fast. And if it reached 90 meters per second, that would be enough to kill you. So if this was actually the speed that the penny reached when it hit you, by the time that it could hit you, it would definitely do some serious damage. Okay? But fortunately for us, that doesn't happen. So what actually happens is, remember that we have air resistance. And because of air resistance, there's a drag force. And drag force is proportional to some constant times the velocity squared. And so what this tells us is that eventually we're going to reach what's called the terminal velocity. And the terminal velocity to calculate it is 2 times the mass times g divided by c, which is the drag coefficient. So it just tells us how much drag an object has. Rho, which is the density of air, and A, this is the cross-sectional area. And it turns out when a penny's falling, it starts tumbling. So a penny actually would be a little bit different than this. Its formula wouldn't look exactly like this. It's a little bit more complicated because it's tumbling and rolling and spinning and whatnot. But it still has the same effect. It still has some terminal velocity vt. Okay, and in the case of a penny, it turns out that terminal velocity vt is about 45 meters per second, which is still fast, and it would hurt for sure. But it wouldn't be. But that's not really fast enough for it to be falling because the penny's so light that it would just give you a pretty good welt on the top of your head. But that's about all the damage that it would do. But let's take a look at how long it would take the penny to reach terminal velocity in the first place. Okay, so to do that, we can use our equations of motion again to say, well, Vy, we want to be the terminal velocity, which is the initial Vy, which was 0. So that's just gt. So the time to reach terminal velocity is just the terminal velocity over g. Okay. The distance to reach terminal velocity, x, is just 1/2 gt squared. So vt squared over 2g. So this is the distance it takes to reach terminal velocity. Okay, so now let's say we want to find out how much time, the total time it would take the penny to fall. So to do this, we say, well, we have the height of the building is h, right? So so we want to fall a distance h minus x now, and that's going to be our terminal velocity times t prime plus 1. So normally you would think we add a plus 1/2 g t prime squared term on here, right? But we don't add this because this increases the velocity, right? But we're not increasing the velocity anymore. Once we've reached terminal velocity, our velocity doesn't get any bigger. So in other words, the time that it takes for it to fall the rest of the way is just h minus x over vt, which is just h over vt minus vt over 2g. So then our total time is just going to be t plus t prime, which is h over vt minus vt over 2g plus vt over g, which is just h over the terminal velocity minus plus the terminal velocity over 2g. And so this would be the total time that it takes the penny to fall. So notice it's very important that we get rid of this term, because this would increase the velocity, which changes how fast the penny's falling. But the whole point of terminal velocity is saying that this terminal velocity is the maximum velocity. So at that point, our equation becomes much simpler and it's much easier to solve.